Welcome everyone. Greetings from the Australian National University here in Canberra. My name is Jay and I look after international relations and partnerships here at the ANU in the areas of sciences, health and medicine. I'm joined today by my colleague Arthur Xu and our speaker for today, Professor Peter Beltner. Please let me begin by acknowledging the Ngunnawal and Ngambri people who are the traditional owners of the land where ANU is located and where we are broadcasting to you today from. And I pay my respects to their elders past and present. Now, let me very quickly introduce our speaker for today, Professor Peter Beltner. So Peter is a professor of theoretical physics and mathematics at the ANU Mathematical Sciences Institute. He's originally from Netherlands and came to Australia in 1995. And that was after spending several years researching and teaching at MIT, at CERN, and at the University of Southern California. Peter is regarded as an expert on the mathematical foundations of string theory and conformal field theory. And in 2001, he was awarded the Australian Mathematical Society Medal. Peter has served on the Australian Research Council's College of Experts and the ERA Research Evaluations Committee, and he is a former director of the ANU Mathematical Sciences Institute. His current research interests include the investigation of mathematical aspects of physical theories, in particular quantum field theories. I'll now hand over to Professor Peter Beltner to tell us about dualities in mathematics and physics. Over to you, Peter.
Thanks, Jay. I'll first try to share my screen. Yeah. Okay, that all seems to be working. So welcome everyone, in particular those students from our partner universities across the world. I should make an immediate statement that this is actually the first Zoom seminar that I'm giving in this way. It's quite unusual for me to just talk to a screen and not see everyone. So I hope that this all goes well and there's also no technical glitches. Of course, I would have liked to see you all in person. But unfortunately, due to the current pandemic, we're not allowed to travel anywhere. So, yeah, that's the best we can do right now. But in the meantime, I hope you're all keeping healthy and that you're soon, or maybe already have been vaccinated, and that we can start traveling and seeing each other in person again soon. Okay, so my lecture is about dualities in mathematics and physics, and I wrote in my abstract something about the unreasonable effectiveness of mathematics and physics and vice versa. Now, this is not a philosophical talk. I'm not going to argue for the effectiveness and certainly not for the unreasonable effectiveness. If you're interested in those kind of questions, I would suggest you just Google it. There's plenty of books written on the matter and also interviews available on YouTube. What I mean for the purpose of this talk is just that physics and mathematics seem to go hand in hand often, and certainly are motivating each other for new developments. So, developments in mathematics are often motivated by developments in physics and vice versa. So the specific developments that I want to talk about are dualities. Now, I realize I'm talking to a very diverse audience. I think probably most of you will be third and fourth year undergraduate students. Maybe there are some master students as well. I'll actually be sort of presenting a talk that gets more and more complicated as we go along, but I hope there's certainly something for everyone in the talk. And as Jay just mentioned, the talk will be recorded. So if there's some piece of mathematics that you're not familiar with, then I would strongly encourage you to just look it up on Wikipedia or a textbook, and then come back to the lecture series and see if you have a better understanding of what's going on. Okay, so now I should be able to change the page. Yeah. Okay, so first of all, I should really tell you what a duality is and why dualities are important. So I'm not, my purpose is not to give you an overview of all possible dualities in mathematics and physics. Of course, I want to focus a bit on my own research and my own interests, also to give you an impression what sort of research is being done at ANU. So as a good mathematician, I should start with a definition of duality. And as a physicist, I won't give you a very precise definition. So for me, a duality for today will be maybe a transformation or a map that relates one object to a dual object. So an object can be a function or something more complicated, and we'll see some examples. And in such a way that this is what is called duality, so the map is its own inverse. Now, duality is usually also used in a more broader sense, where you not necessarily have to go back to the same situation after applying the map twice, but it can be up to some signs which are really irrelevant. Anyway, basically, so duality is a relation between two objects with an invertible map. So why are dualities interesting? Well, from one point of view, they're interesting because it allows us to do computations for these objects, maybe some functions that you want to solve differential equations for, or something like that, by means of doing it for their dual objects. So if a calculation is difficult, or you're not able to do the calculation for the object itself, maybe by a duality you can go to the dual object, do the calculation there, and once you're done with the calculation, to go backwards to the original objects. So for instance, this happens often in quantum field theory, where calculations that you can do perturbatively are quite straightforward by just calculating Feynman diagrams or other techniques. But for the dual object, this might correspond to something where things are strongly coupled and you can't do calculations by perturbation theory. So this is a way of actually getting hold of strongly coupled systems like black holes maybe, or certain other phases of matter, which are strongly coupled, where you can't do direct computations by perturbation, but if you find a dual object where the coupling is weak, you might be able to do the calculations there, and then afterwards transfer the calculations back to the original situation. So that's one of the most important examples. So in this talk, I want to talk about a particular duality, which is called topological T duality. So this duality arose in string theory, but it actually is very closely related to other dualities in mathematics. And in fact, your physics intuition can be very useful in formulating conjectures on the mathematical context, and some of those conjectures can actually be proven. So this topological T duality is something that's both very useful in mathematics and in physics. So what I will argue, I'll first give some examples of dualities, but what I will argue is that topological T duality is actually just a form of Fourier transform. It's a more complicated form of Fourier transform. Now, I believe that most of you will be familiar with Fourier transform, so hopefully you can see the analogy. Okay, but first some examples. So the first example of a duality which you have in mind is something that certainly every physicist will be familiar with. This is a duality for Maxwell's equations. So Maxwell's equations are equations for an electric field and a magnetic field. Oh. Now that was not intended. So sorry, I need to now. Okay, sorry for that. We're bound to have some technical glitches. Anyway, so electric fields and magnetic fields. And the Maxwell equations are equations for the divergence of the electric field and the curl of the electric field, as well as an equation for the divergence of the magnetic field and the curl of the magnetic field. Now these equations look very symmetrical, except that for this rho and this j here, which are the charge density of electrically charged particles and the currents of electric particles. So if the currents and the charges of electric particles are zero, then in fact these equations are completely symmetric under the exchange of E and B, or rather, you need a minus sign there, but that's not very important. So this is a so-called duality, because if I do it twice, then I go back to the original situation. If I want to have electric charges and magnetic and electric currents, then of course I can add terms here like a magnetic charge density and a magnetic current density, and then it's even symmetrical under the situation that I have electric and magnetic currents in my situation. So this is called electromagnetic duality, and I claim this is a well-known duality in mathematics, where it's called Hodge duality. So Hodge duality, and here I have to introduce a bit of a different notation. So Maxwell's equations are much easier to write down in terms of differential forms. So differential forms are objects like dt, dx, dy, and you can multiply those, and you multiply them antisymmetrically, and such objects are called forms. So I hope that most of you will be familiar with forms. Now you can put the electric and the magnetic field in terms of a two form, so things which contain products of two one forms. Or if you want, you can put them into an antisymmetric tensor, an antisymmetric two tensor F. And the specific form for that is given here. And in that notation, the Maxwell's equations just take the following form: df equals 0. So the d is a differential of a form. So it's just like taking a derivative. So these are the encoding the curl and the divergence of my electric and magnetic field. So that gives me two of the equations, and the other two equations are given in terms of another two form, which is obtained from the first two form by a procedure called the Hodge dual. So this is just a map that gives you out of a two form another two form. Now obviously these equations are completely symmetric under the exchange of F and the Hodge dual of F. So Hodge duality is of course very well known in mathematics and has all kinds of beautiful applications, for instance harmonic analysis, where you can do decompositions of forms into harmonic forms and other objects. So this is one particular kind of duality, and this has many generalizations. So this is a duality in the classical Maxwell theory, but you can also go to the quantum theory and talk about non-abelian duality. And these kind of dualities are present in string theory, where they're called S-dualities. And they're very useful in calculating dualities between strongly and weakly coupled systems. My duality that I want to discuss today is actually much simpler than this. As a first indication, let me tell you about a duality between, well, in physics, between Schrödinger and Heisenberg pictures for a quantum mechanical system, which in the mathematical context is related to Fourier duality. As I said, the T duality that I'm going to be discussing is related to Fourier transform. So a case where you have an obvious symmetry between, say, momentum and coordinates, so is the case of a harmonic oscillator. So the Hamiltonian H for harmonic oscillator is given in terms of a kinetic term, E squared over 2m, so this is just a kinetic term, plus a potential term, which is 1/2 kx squared. So classically, the momentum is just the velocity of the particle. So this is a one-dimensional system. So just m times the velocity. But in quantum mechanics, we replace coordinates by operators acting on some Hilbert space, and the operators x and p in that case have to satisfy this commutation relation. But it's obvious that the Hamiltonian has a duality namely replacing x by p and p by minus x, as well as interchanging m and 1 over k. So usually mathematicians don't care about m and k, they just normalize everything to 1. So it's really the interchange of p and x. So quantum mechanically, what we're doing here is representing p and x by operators acting on some Hilbert space. And the Hilbert space in the Schrödinger picture is a set of square interval functions of one variable, where x acts just by multiplication and p acts by this differential. So this situation satisfies this commutation relation x p. And I could have done it differently. I could have represented the Hilbert space by functions of p, where p acts by multiplication and x acts by taking a differential with respect to p. And these dual pictures are just related by Fourier transform. So a Fourier transform of a function of x is the following expression. I just multiply it by this exponential, integrate over x, and I get a function, a dual function of p. And the two pictures that I've discussed here, this Schrödinger picture in which p acts as minus I dx, and x acts by multiplication, and the other way, I just relate it by Fourier transform. A Fourier transform has an inverse given in the second line here, so this is really a duality in my sense. If I would apply, so you notice the inverse has the inverse sign of the exponential. If I would just apply this transformation twice, I of course get the function back, but at the point minus x, because I multiplied by the wrong sign exponential. But this is what I meant by applying the map twice. You might go back to the same situation, maybe up to some minus signs. Okay. So finally, I want to talk about something which is also relevant from a more general construction. That is the case of a particle on a circle. And that turns out to be also related to Fourier transform, in particular Fourier transform of theta functions in a mathematical context. So if you have a particle that moves on a circle of radius r, then its momentum is going to be quantized. That's just Bohr's quantization rule. In simple terms, you want the wave of the quantum mechanical system to fit into the circumference of the circle an integer number of times, this number n here. So that quantizes the momentum of a particle in units of 1 over r. So if you then write down the partition function for the system, so the partition function in a statistical mechanical sense is just a trace of e to the power minus beta. Beta is 1 over k times the temperature times the Hamiltonian. So it's just a trace of this Hamiltonian of a free particle, p squared over 2m, and you can write it as this infinite sum over n. All the momenta that you have in the spectrum are labeled by n. And I've introduced here an alpha prime to get rid of some of the other constants. But essentially, it's just a sum over n with exponential of n squared. Now, Fourier transform, as we've seen, relates momentum to sort of dual momentum. In this context, for partition functions, what you can do is use the Poisson resummation formula, which tells you that for suitable set of functions, the sum over all integers of a function is just the sum over integers of the Fourier transform of that same function. So we have here a very special function, which is just an exponential function of basically the n squared. Now, it turns out that this function, which is well known in Fourier transform, is essentially its own Fourier transform. So if you use that, you'll see, and you do some rescaling, but you'll see that the partition function of a particle on radius r is the same as the partition function of a particle on radius r hat, where r and r hat are essentially each other's inverse. So this is not quite true. You need to correct by some factors here. So it's not true that the system of a particle on a circle of radius r is exactly the same as the system of a particle on radius 1 over r, but they're closely related. And we'll see that actually my generalization will be an exact relation between spectrum on the one hand side and the spectrum on the other side. Okay, so this was just warm up. I want to now slowly introduce what I call topological T duality, and I'm doing that by just rephrasing Fourier transform a little bit. So Fourier transform is well, I mean, there's different forms, but let's say we have a function, periodic function, so a function on the circle to R. And Fourier transform is a transformation which builds out of this function a function on the integers. And basically because, opposed to my earlier formula, I have to take integers here because this exponential needs to be well defined. So if I go around the circle, you need to get the same value. But this has a nice inverse as well. And as I said, another version which I introduced before is if I have a suitable function from the reals to the reals, I can do Fourier transform by multiplying it by e to the power I minus I px and get a function of the variable p. And there is an inverse where I take the function of the variable p, multiply by e to the power I pi x px and get the original function back. So this has a vast number of generalizations. So we see we can do this for the circle, going to functional R, functional R to other functions in R. And I'm not formulating this very mathematically precise. Of course, the set of functions I do this for have to be such that these formulas are well defined. But that's not relevant for my talk, so I'll keep that in mind. So a vast generalization is not just to take S1 or R, but take for functions on a general, well, locally compact abelian group. So R and S1 are both abelian groups, which are, well, S1 is compact, but R is locally compact. You can define Fourier transform in the same way. You take the function, you multiply it by this exponential, and you integrate over the group. And this gives you a function on the other side, which turns out to be a function on what is called the Poincare dual group, G hat. So the Poincare dual group is defined as the set of homomorphisms from G to U1. So, so it's also known as a character. So a character, so the fact that it's a homomorphism, if I add them into G, so I've written the abelian group action of G as an addition, and then apply the map, it should be the same as first applying the maps and then doing the group operation in U1, which I've written as a multiplication. So this is the definition of a homomorphism from G to U1. So what Fourier transform does is transform functions on G to functions on the Poincare, the Pontryagin dual. So the examples we had was where G is S1 and the Pontryagin dual is the integers, and then the multiplication that I need in my integral is just e to the power I n x, which for every n is actually a character of S1. You can easily check that it satisfied my my homomorphism relation. And the other example is where I have G is R and the Pontryagin dual is in that case also R, and then the characters are given by I in the power e in the power I px, where p is an element of the Pontryagin dual. Okay. So in some sense, we can think of these functions as a basis for all the characters, so sort of as a universal character. Now, these functions are not functions on the group or the dual group; they're functions on the product, and this is something which is sort of amazing amazing thing of Fourier transform. So let me go back to the definition of Fourier transform. So let's take this definition. So these formulas all look well, but actually there's something very strange going on. You can think of these integrals as sort of black boxes of creating an f hat out of f. But inside this black box, I start with functions, just functions of x, and then my dual function is a function of a completely different variable that doesn't seem to have much to do with x. But inside this black box, I actually multiply by a function of both variables. So I take a function of one variable, then somehow multiply by a function of both variables, integrate out one of the variables, and end up with a function of the other variable. So mathematically, this is known as what is called a correspondence. So here's Fourier transform in terms of abstract mathematical notation. So I start with a function here, a function on G, that's this f here, and then I want to multiply it by something which is a function of both G and G hat. And so what I do is I take that function and consider it a function of G and G hat just by making the G hat dependence trivial. So that's this thing here. I pull back the function to the function on G cross G hat. And I multiply by something, this universal character, this exponential e to the power I px. And then I integrate out one of the variables and get a function over here. That's what it's called here, pi hat. So, you get a relationship between functions here and functions here by having an intermediate function space, which is this correspondence, and just taking functions here, pulling them back here, multiplying them by something, and then pushing them forward to get a function just of G hat. So these correspondences are quite general, and the duality that I'll be constructing for you shortly will be just such a correspondence. In that sense, it's just an analog of Fourier transform. So this was just Fourier transform for functions. This new duality that I'll be discussing, this T duality, is in some sense a geometric version of harmonic analysis. So a geometric version where you replace the functions by geometric objects, or maybe by not by objects, but maybe by certain classes that are associated to these objects, such as cohomology or K-theory, or you can make it as complicated as you want. Okay, so we're not going to go one step up in mathematics that's required. We need to know a little bit about cohomology. So cohomology is something which is defined in terms of differential forms, at least for the purpose of my talk. So a differential form we've seen before. My electromagnetic field could be written in terms of a differential form. Now a differential form can be acted upon by a differential which squares to zero. So what we can do is we can look at the kernel of the differential, and a subspace in the kernel of the differential is the image of the differential, because if I have something in the image, then it is in the kernel because d squared equals 0, and this object is called the cohomology of the differential d. So it turns out that the cohomology of a product space, so I'm thinking here of P being my, say, space-time. Space-time is a manifold M times a circle. And we'll construct a duality here, which is a duality for this cohomology theory, which closely resembles T duality. Closely resembles Fourier transform. Okay, so first what I'm using here is that the cohomology of such a product space is just the product of cohomologies of the individual spaces. Now, the cohomology of S1 is very easy. The cohomology of S1 is just sitting in degree 0. So sitting in, H. I should have an eraser somewhere, but let me just try to. HI is just R if I equals 0 or 1, and 0 otherwise. So the cohomology of the circle is just it's just sitting in the 0 forms and the 1 forms, and in each of those degrees, it's just basically a one-dimensional vector space. So if I look at the cohomology of degree n here, it comes as in terms of two sets. It comes in terms of the nth cohomology of m, which I've combined with the zero cohomology of S1, or the n minus first cohomology of m, which I've combined with the first cohomology of S1. And you can do this not just for cohomology, you can also do this at the level of forms. You then have to go to invariant forms, so forms that are invariant under the action of S1. And then basically a form can be written as an invariant form on P, which is m cross S1, can be written either as a form on P, or sorry, either as a form on n, or as a form on m cross S1, where the form is a form on m wedged with the generator of the first cohomology of S1. So the first cohomology of S1, I mean, if theta is a coordinate on S1, then of course d theta is well defined, because if you have to identify theta with theta plus 2 pi, it drops out of the differential. So this explicitly gives you forms which are either in omega n, or a form which is in omega n minus 1, and the cohomology of those forms will be giving you this decomposition. Okay. Now here's my duality. I claim that the cohomology of P is isomorphic, or is dual to cohomology of another space, P hat, which is also m cross a circle, but a different circle, a sort of dual circle. And the isomorphism is not an isomorphism which preserves degree, but it shifts the degree by 1. In other words, it's not a form which, it's not something which preserves the degree. I have to combine the even degree cohomology and the odd degree cohomology. So that's what I call H0 bar and H1 bar. And then the map is explicitly just given by mapping the forms on P that live totally on M to something that lives on M cross the generator of the dual circle. And similarly, the other object that I had on P, which is the form on M times the generator of the circle, maps to this dual object. So you can see this map doesn't preserve the degree, it preserves the degree modulo 2. So we can write this map more succinctly in the following way. So you can check that if I have omega, if I have a form which is one of these types, that if I multiply by this 1 plus a 2 form and integrate over S1, so I integrate away the theta, that this precisely gives me these two formulas. So if capital omega is of this type, then if you multiply by this 1 plus 2 form, well, the multiplication with the d theta hat, which just gives antisymmetric in d theta hat, which doesn't exist. So it's only this term it contributes. And then I integrate away the d theta. So anyway, so this is easy to check. But this is just Fourier transform, because I can write it slightly differently. I can write as 1 plus d theta wedge d theta hat as the exponential. So the exponential is just usually, as usual, defined as 1 plus, well, as the sum of 1 over n factorial x in the power n, but then for where x is a differential form. But it stops after the first two terms, because things like d theta wedge d theta are 0. So this looks exactly like Fourier transform, where I take a form on P, I consider the form on P cross the dual space, and then I multiply it by some object, and then I integrate away the one circle. So this object I multiplied with is this exponential here. And we've seen in the case of functions that exponential had a particularly had a canonical meaning as a character of some group. But here it has a similar meaning. Well, first let me write this down in the same way as we've done Fourier transform. So we have this space P here. We had a form here. We're going to consider, that's the form omega here. We're going to consider this as a form on M cross S1 cross the dual circle by pulling it back. So basically just taking the dependence on all the S1 hat variables to be trivial, then I multiply it by this e in the power f, which I had in my formula, and then I integrate away the S1 variable, so I get something which is a form over there. And not only does the correspondence look the same as what I have for Fourier transform, it turns out that this e in the power f, so f was d theta, which d theta hat, is actually also a canonical object. It's called the it's a curvature. It's a two form. It's a curvature of a particular line bundle. So you're making another step into the more complex mathematics. So you maybe not know what a line bundle is, but anyway, there's some canonical object of which f is the curvature. And in fact, this canonical object, this Poincare line bundle, is sort of the generating bundle for all possible line bundles. And this e in the power f is in mathematics known as the Chern class of this line bundle. So it has a very geometric meaning. So in fact, having an expression like this in terms of classes for bundles suggests that such a transform should be possible for the bundles themselves as well. So you might envisage having a vector bundle, pulling it back to some correspondence space, multiplying it by some line bundle, this Poincare line bundle, and then pushing forward to get a dual vector bundle. Now this doesn't quite work. The problem is with this map push forward. It turns out if you go to something that's kind of equivalence classes of vector bundles that things do work, and these kind of equivalence classes of vector bundles are called K-theory. So now I'm already quite deep into some advanced algebraic topology course. So let me not go into more detail about this. So time is running quickly, but I want to tell you where this comes from in physics. So this comes from string theory. If you look at closed strings, so these are loops which come together, and you look at how they move in space-time. So space-time was my m cross S1, so just a lower dimensional space-time times a circle. So then, in particular, closed strings are defined by mapping this sigma, this world sheet of a closed string. So this is a closed string. If it moves in time, it maps out some two-dimensional surface sigma. Part of the data of a string theory is to describe how this surface sigma sits inside my space-time, my physical space-time. Now, as we've seen, for particles that are moving on circles, the momenta are quantized, and similarly, you find that the momenta for strings, which are in the direction of S1, are also quantized in units of 1/r. But for a string, something very specific happens. So strings not only have momentum, but they can also wind around circles. So it's very easy to envisage a closed string, as I had here, which inside my space-time M, if there's a circle in this space-time, then the string can just wind around this circle, and that's a stable configuration because I can't shrink that to a point without breaking the string. So a string also has winding modes. So essentially, just telling you, if I go around the string, if I go around this loop here, then it can differ in space-time by m copies of r, and I'm ignoring the factors of 2π here. So in an analogy with the point particle, where I had a contribution to the Hamiltonian, which was just p squared over 2m, so something like n squared over r squared, I now have contributions to the spectrum which come from these winding modes. And what you can see, obviously, here, so there's many more modes. Of course, a string can oscillate, and that gives you contributions to the spectrum as well, but they don't depend on r. Oscillations are something local. All the r dependence of the spectrum of the string sits in these two terms. And obviously, there's a duality going on here. R goes to 1/r. So in the particle case, we have seen that indeed this r to 1/r did show up as a consequence of your Poisson summation formula, but wasn't an exact symmetry of the theory. But here, because I have this term over here, the energy spectrum is just invariant under R goes to 1 over R. So in fact, this is not just true for the energy spectrum, it turns out to be completely true for all aspects of the string theory, like scattering amplitudes, etc. So it actually turns out that a string theory on M cross S1 is completely equivalent to a string theory or this closed string theory on M cross the dual circle, where the dual circle has a radius 1 over R. So this is the analog of this duality that I've described in terms of forms in my previous example. Now, I'm doing here more than forms. I'm doing actually something dynamical. So it's more than topology what's happening here. Because I didn't, in my topological consideration, didn't see this R. Of course, that is because the circle and the dual circle, even though they have different radii, they're topologically the same. But this is essentially where this duality on cohomology comes from the string theory. Now, this can be vastly generalized. And yeah, I should be mindful of the time. I want to certainly finish up in 5 minutes, so I'm not going to be able to get through the whole talk. But maybe we can post the complete set of slides so that if you're interested in hearing the full story, you can just go through the slides. So this is the most difficult mathematical part of it. Now I'm going to generalize S1. So initially I had just a space-time M, and over each point in M I had a circle. So that was M cross S1. But of course, these circles can somehow be twisted, and that's what's called a circle bundle. So this is my picture for a circle bundle. So over each point in M, I do have a circle, but they don't line up nicely in an M cross S1, but somehow when I go around the base manifold, I start twisting the circles. So you can think of this as sort of a circle generalization of a Möbius strip, where you basically have so a Möbius strip, you basically have a circle, and over each point you put an interval, but when you go around the circle, you glue the interval at the end, but with the original interval by twisting. So you get something which is called a Möbius strip. So this is a generalization of that. So instead of doing duality on M cross S1, I can also do duality on these circle bundles, so things which are locally M cross a circle. And the other generalization is that I can couple my string to an analog of an electromagnetic field. And in this case, the analog is not this flux F, this electromagnetic flux that I introduced in one of my first slides, but so it's not a 2 form, it's actually a 3 form. So there's 2 generalizations here. One is that I can go to non-trivial circle bundles, and the other is I can couple my strings to a background generalization of electromagnetic flux, which in this case is a 3 form. Now, so a bit of algebraic topology, such circle bundles are topologically classified by a 2 form in taking values in the second cohomology class, and by electromagnetic field analog is classified by something which is a 3 form, but on the bundle space P, while this element that classifies my circle bundle is sitting on the base M. It turns out that this T duality can be generalized to this setup, and that the dual of my configuration with a circle bundle P and a flux H is another circle bundle, but some circle bundle which can be topologically different, and the dual electromagnetic field, a dual flux. And there's a simple formula for that. So the formula essentially is that the dual 2 form characterizing this dual bundle is given by taking my 3 form and, well, by star tensor for integrating over the circle. So if I have a form on something, say a 3 form, and I integrate over my original circle, then I get a 2 form out of it. I lose one of the variables. And symmetrically, if I have the dual flux, the original bundle F can be obtained by integrating over the dual circle. Now there's nice topology behind this. There's algebraic topology behind this, which I'm going to largely skip. I just maybe want to mention for people that know a bit of algebraic topology that this is precisely what's happening in what is called the Giza sequence. So the Giza sequence is a sequence of between cohomologies where P is a circle bundle over M, and these cohomologies of P and M are related through a sequence in cohomology. And this map here that I've defined, so my H was sitting in here, my 3 form on P, the dual circle bundle, which was characterized by F hat, is just this map here. And so the fact that this sequence in cohomology is exact means that if I do the following map over here, I get 0. But then I can, I don't know, I keep losing my annotations, but then I can look at the original object F here. And again, I know from the first sequence that this maps to 0. So exactness gives that it comes from something that lives over here, which I've called H hat. And of course, H hat here in this setup is not unique, but it's unique up to an element that comes from here. So you need to fix that element, but that's quite easy to do. So I'm not going to go through much more. I just want to give you one final example of what's happening here. So if I think of the simplest example where I have both non-trivial circle bundles and non-trivial electromagnetic backgrounds, so non-trivial H3, it is the case of circle bundles over S2. So my P is here a circle bundle over S2. So circle bundles over S2 are classified in terms of the, as I said, the second cohomology, which in this case turns out to be the integers, and 3 fluxes on P, so over here, are also classified by integers. It turns out that my duality just interchanges these 2 integers. So as a very simple example, I can take S2 cross S1. So this is the very first example that I discussed. In that case, if I take 0 magnetic field here, so the 0 element, 0 integer here, the duality just gives me the same space back. So topologically, we had seen it already. If you do more than topology, the radii of the 2 circles are actually related by r goes to 1 over r, but you don't see it in this setup. But here's something interesting. If I take S2 cross S1, but I take 1 unit of flux, so strings moving on S2 cross S1, but with 1 unit of electromagnetic background, then the dual turns out to be S3 with 0 units of electromagnetic background. But S2 cross S1 and S3 have completely different topology. S2 cross S1 is this, I don't know if you know how to draw it, but it's some higher dimensional analog of a torus, while S3 is just a 3 sphere. So topologically, they're different. Yet what I'm saying here is that the string theories that are described by the spacetime S2 cross S1 with some flux background and a string theory moving in S3 without a flux background are indistinguishable. So string theory can't actually tell you about the topology of space-time. There are space-times which are indistinguishable by string theory. And that's probably a good place to stop. So this has many generalizations, and I've hinted on some of the mathematical consequences. You can just, for instance, use the fact that these are dual by to compute cohomologies of K theories or K theories on one side from the other side. And well, this example is quite trivial, but a more complicated example, that is really an effective mathematical way of computing difficult objects just by transforming them under this duality to something simpler. So as I said, I'm happy to post the rest of my slides on on the web. Of course, you can also refer to my papers, which have many more details. And I hope you at least got the Fourier analogy out of my presentation. And if you ever hear about T duality, then and want to know more, you know, okay, maybe I should go back to these slides and catch up on my Fourier Transform and on differential forms and those kind of things. So let me stop here and just see if there's any questions.
Great, thank you very much, Peter. That was very informative talk. There's a couple of questions in there already, Peter. I can take the first one, which is asking when will this video recording and the slides be made available. So sometime next week, we'll just polish up the recording and this will be posted where you would have registered for the talk. And of course, if you've registered, we'll send you an email as well that, you know, the recording is available. And we'll try and include as many of Peter's slides in there as possible. Great. So that's that. Peter, do you want to take the next question?
Yeah, I clicked one of the questions. So the question by Churchill is, how are these dualities useful in the area of astronomy or cosmology, black hole physics, for instance? So I put back up the slide where I said that string theory on a circle of radius r is indistinguishable from a string theory in radius 1 over r. So this has some cosmological implications, because if we believe in a Big Bang, we think the universe started really out of a point, out of something with radius 0. But what I'm saying here is that string theory, a more natural interpretation for radius 0, or very small, would actually be an interpretation in terms of a very big space. So in some sense, cosmology with strings is different, because things like Big Bangs, you might just see them more naturally as having just a very big universe. Now, of course, this is my example with the circle is a very, very simple toy model, but these dualities are present in more complicated models of space-time as well. So definitely here, there's something going on. Now, black hole physics, yeah, again, of course, there the R2 over R might play a role, but most applications to black hole physics come from a different kind of duality, the so-called S duality. So this duality, for instance, has been used to calculate the entropy of a black hole. Now, black hole is a very strongly coupled system. So it's both very heavy and very strongly coupled. So it can only be described by quantum theory of gravity, and you can't treat it as classical gravity because it's very massive. You can't treat it classically because it's rather than quantum mechanically, because it's very strongly coupled. But it turns out you can apply a different kind of duality and describe it in terms of a weakly coupled object. You can do the calculation of entropy in that weakly coupled object, and then just translate it back to the black hole in your physical system. And it actually turns out that this confirms a formula for black hole entropy that was discovered many decades ago by Hawking, just on the basis of empirical evidence. So yeah, that's my answer to this question here. I hope that was sufficient.
Thanks, Peter. So we've got a few minutes for those attending. If you want to please put your questions through now.
So the fact there's no questions is either always a good sign that everything was completely clear, or a very bad sign that nothing was clear at all and that you don't even know what question to ask. I hope the truth is somewhere in the middle, though. But
just for the sake of recording, Peter, do you want to just maybe flick through the rest of your slides so we can capture that in the recording? So
you can't post the slides separately as a slide deck?
Unfortunately not. We may be able to email them through to everyone, but if you can just go through the recording and people will be able to pause and play the recordings.
Okay, so I'll do it quite quickly. This I've had. So I discussed this example. So this is the stuff that I didn't get to. So I go through it quite quickly because you can pause it on your own time. And that's all.
Great, thank you. I think there's a couple more questions there already.
Okay, so this is really a question about studying algebraic topology. So, so the best book to start that I tell all my students to start reading is the book by Bott and Tu. It's called, I have a copy here somewhere. But if you look for the authors Bott, Raoul Bott, and Loring Tu, they've written one book together, and that's an excellent source. And it, for instance, explains this Giza sequence that I refer to as the mathematical ordinance of T duality. It explains it in all detail. But there are many other good books. There's also a book by Hatcher, a bit more advanced, but also more recent, so using more modern techniques. Again, there are many more. I would suggest talking to your lecturer or lecturer at your university, whether they have any particular recommendations. Okay, so the next question is, how are the other dualities helpful? T duality, as you said, has a Fourier series analogy. Can we do something like that for the others? Well, so S duality is one duality which I mentioned that has its origins in electromagnetic duality. But unlike T duality, is not on such a rigorous mathematical basis, because essentially what T duality does, it doesn't go to a strongly coupled regime. So because we have problems of proving anything rigorously mathematically in strongly coupled regimes where we don't have perturbation theory. So S duality is believed very strongly by all people working in the field, but mostly because of some checks that we can do, but not because we have a full proof. I don't know the other dualities. There's many other dualities like ADS duality, which is like a holographic duality, where some gravitational theory on some space can be dually described as some quantum field theory on the boundary of that space. Again, there's a lot of circumstantial evidence that that's correct, and that can be used to do calculations in strongly coupled systems with, and not just string theory, but you can model, for instance, other strongly coupled systems in condensed matter physics, for instance, by such string-like systems, and do computation in condensed matter physics for strongly coupled systems, and the results there are also very promising. But yeah, as something as well known as Fourier Transform, that I don't know for the other dualities. Okay, so this is a bit of an open-ended question. You talked about the strings as loops and the models and the modes being winding and the normal momentum associated with them. So how is this different than loop quantum gravity? What are the other possible modes we can have the strings in? What's your personal opinion regarding the future of string theory? So maybe I won't answer all of this. So in loop quantum gravity, we actually don't, that's true that loop quantum gravity is also described by mapping loops into spaces, but we don't really have a good understanding how general relativity follows out of loop quantum gravity. So we don't really have a good classical limit that we can take there. So, but certainly things like winding and even maybe dualities might occur in the quantum gravity as well. So the other modes I'm talking about are so the global modes are really the momentum and the winding modes, but there's other modes of a string like oscillations, and they of course are something which can happen locally. So they don't see the global aspects of your space-time. They just happen locally, and locally you can't see whether the space-time has a hole in it or not. So really the topological properties are sitting inside this momentum and winding interchange. Okay. So there's a more detailed question by obviously a more advanced person. Is string theory on ADS5 plus S5 with fluxes dual to strings on some other background with fluxes? So I'm not completely sure about this particular example, but there are examples for ADS spaces with multiplied by other spaces which do have this T duality, and most dualities are where you have fluxes on both sides. So in our paper we have a few of those examples. So if you're interested in examples, then I would suggest you look up one of my papers on this. Dualities have a connection with category theory. Yeah, definitely. So dualities are really related to what is called higher geometry. So these fluxes that I'm talking about are really not connections on line bundles, what the usual electromagnetic description is, but they're connections on higher geometric objects called gerbs. And gerbs, well, I have a categorical definition if you want, but yeah, but all this higher dimensional analogs of what you see in electromagnetism are just versions of particular categories. That was a good question. So maybe I'll take one more question. Is there any possible application of dualities in studying high TC superconductivity in condensed matter physics? Yes, I did talk about applications in condensed matter physics, and one of the applications is to high TC superconductivity. Now, these applications are, of course, always for sort of idealized models. So I'm not enough an expert on these kind of dualities to say whether these models are close enough to physical reality or not. But yeah, high TC superconductivity is a strongly coupled system, and certainly these dualities can be applied to those scenarios. Okay, so maybe I should do the last question. Why we don't discuss duality in early science classes? Although I'm a master's student, this area seems to be new to me. Yeah, well, I mean, so things like electromagnetic duality and Fourier Transform are discussed in undergraduate classes, but maybe my take on it was slightly different, and that was in order to generalize it to other things than just functions. But this whole duality stuff arising out of string theory is really something that's been going on in the last 20 years, 30 years. And it's all really very new there. I mean, you can find it in some recent monographs on string theory, but I think it's all a bit too new to discuss in a standard undergraduate program. Now at ANU, we do have occasionally courses on string theory where these things are mentioned. And at other universities have that as well. So, so hopefully this answers your question. And I think we probably should stop here, Jay.
Yes, thank you very much, Peter, on behalf of everyone. Thank you once again for the talk and for taking all of those questions, answering them. For all those attending, thank you for coming along and joining us for this talk. have a great rest of the day. And Peter, thank you. And we'll see you. Great. All right. Bye-bye.
Thanks, everyone. Bye.